Hello everyone, I'm Pengzhi Huang from Cornell University, and today I will present a work titled Efficient Privacy-Preserving Machine Learning with Lightweight Trusted Hardware. This work is a collaborative effort with Tang Hang from Virginia Tech, Yueying Li from Cornell University, Elaine Shi from CMU, and my advisor Edward Se from Cornell University and NVIDIA. In many scenarios, multiple parties are involved in a single computation, often utilizing data from various sources. For instance, consider personalized advertising, where user profiles are derived from multiple datasets. The parties involved want to ensure that sensitive user information remains secure while contributing to the computation of the secure function. This need for privacy and security in joint computation is quite common. There are several cryptographic techniques to address this issue, for example, homomorphic encryption and also multi-party computation. Today, I'll just focus on secret sharing-based MPC. As shown on the right, there is a simple example of two-party secure computation of an AND function using secret sharing-based MPC. Here, the secrets x and y are single bits split into two shares, x0, x1, y0, and y1, distributed between Alice and Bob, the two parties. For Alice and Bob, they have the share x to be x equals to x0, xor, x1, y equal to y0, xor, y1. Additionally, they have this A, B, C as the so-called beaver triple to perform single bit AND operation. As we can see, parties holding only the shares of the secrets x0, y0, or x1 or y1 cannot actually output a correct result without any communication with each other. The primary challenge for MPC is actually the need for communication during this whole process. The operations in secret sharing-based MPC can be generally divided into linear and nonlinear operations. Linear operations are less communication intensive. Some, like additions, can even be performed locally, while some, like multiplications, will require a round of communication mostly. For nonlinear operations, which are common in machine learning, cheap in computation, are far more expensive and complex in MPC, often due to communication, which require sometimes multiple rounds and tons of data to be communicated. As shown in this example for the execution time of AlexAct under one GPU setting with the classical MPC protocol Falcon, the nonlinear layer take up to like 95% of the total execution time. The primary overhead of this is due to communication. In addition to cryptographic solutions, hardware solutions like trusted execution environment are often used to protect data integrity and confidentiality. Many commercial TEs are available, assuming that they assume that the enclave or trusted zone is unbreakable. Computations can be actually performed securely and efficiently inside of these TEs. However, TE have their limitations. In recent years, we have seen the discovery of numerous security vulnerabilities, primarily due to TE's complexity. It is relatively more challenging to secure a general-purpose TE compared to a tiny piece of trusted hardware for something like TPM. For more detailed discussion in this section, I would refer the audience to our paper. The intuition behind our work is to combine MPC and TE to leverage their respective advantages. What if we could create a simpler, less complex trusted hardware to handle the computationally light yet communicationally heavy nonlinear operations in MPC? By simplifying the trusted hardware, we can reduce the trusted computing base, making it more secure, and also reduce the deployment cost. Thus, we propose our scheme called STAMP, an efficient, privacy-preserving machine learning framework with lightweight trusted hardware. STAMP stands for Small Trusted Hardware Assisted MPC. The structure of this scheme is straightforward. In a typical three-party MPC setup, all several parties do not trust each other. They operate on secret shares and carefully manage the communication to prevent any leakage during this case. Then we introduce LTH to each party, acting somewhat like a trusted third party. The LTH generates a shared set of secret keys via key exchange protocol, creating pseudo-random maps to encrypt the secret shares that can only be decrypted within the LTH. The untrusted server or CPU of each party still interact with the LTH to handle their communication, but still the pseudo-random masks prevent any kind of data leakage during this process to untrusted entities. The setup allows the LTH to handle the nonlinear operations by directly decrypting all the secrets inside of them and mostly compute them in plain text. The SAMP protocol combines a three-party MPC with LTH with the honest majority assumption still. The correlated randomness generated by shared keys in the LTH make them function as a trusted third party as a whole. We securely offload the nonlinear operations to the LTH, optimizing the entire process. STAMP involves initialization and mostly protocols for linear operations and nonlinear operations. Our main contribution lies in the efficient handling of the nonlinear layers while also doing optimization on the linear operation part. To ensure the security, the initialization phase established a chain of trust based on three assumptions. Manufacturer assumption, first of all, the manufacturer should be trusted and the verified LTH should not be easily compromised. Secondly, the cryptographic assumption that the key exchange protocol, or more precisely Diffie-Hellman key exchange protocol, it is secure. The third is the pseudo-random function assumption that the pseudo-random function we use is actually secure or say it exists. One of the more complicated protocol within STAMP is the one for softmax operations. We do aim to avoid polynomial approximations, but directly floating point computations are also too much of a burden for our lightweight trusted hardware. The hardware targets the capabilities similar to a TPM module, which isn't powerful after all. Directly computing softmax within the LTH wouldn't achieve the desired throughput. So instead, we compute the exponent computation on pseudo-random mask shares using the more powerful but untrusted CPUs. The multiplied values are then sent to the LTH, and all the remaining operations to be done are much simpler. Of course, there are some problems of overflowing, and the result actually might not even be correct due to the missing modular operations when the exponents are individually computed on the shares. We designed a protocol to monitor and solve both of these issues. Many other crucial functions are also supported by STAMP and which are widely used in deep learning like ReLU batch norm, making this whole protocol actually practical. And furthermore, to optimize the linear layers, we also merge the end of multiplication operations with these subsequent nonlinear layers. At the end of multiplication, truncation is often required because we use integers to represent fixed point numbers. The truncation is necessary to maintain the precision consistency during this whole process. Since truncation itself is also a nonlinear operation, we can merge it with the following nonlinear operations, allowing all the computations to be handled within the LTH simultaneously within one round of communication, eliminating the need for multiple communication runs if we do it in the classical way. Other optimizations, such as balancing and splitting the workload, are also implemented, and we refer the audience to our paper for more details. Our theoretical analysis also show that the communication overhead of the STAMP protocol is significantly smaller than the state-of-the-art MPC protocols in terms of both communication rounds and communication volume, with the cost of extra local communication between the CPU and GPU. We also built a prototype and evaluated its performance through the extensive experiments we set. Our protocol supports malicious security and semi-honest security. We utilize GPUs for matrix multiplication in neural networks, and it is also compatible with various models, including state-of-the-art deep learning models. We conducted a very comprehensive experiment under multiple inter-party network environmental parameters and plus different assumption of the hardware power to see how all these parameters would affect the result. Our results demonstrate significant speed improvements compared to existing frameworks. We compared our protocol to 9 models, here we are only showing 3, under various settings. When the communication is slow and computation is fast under WAN and GPU, our model achieves a speed up ratio ranging from 6 to 66 times. We also include comparison numbers with solutions utilizing SGX as a reference below. Furthermore, we analyze the communication during the entire execution process, showing that STAMP significantly reduces communication compared to the previous MPC protocols, with the cost of some additional local communication between the LTH and the CPU. Returning to our initial intuition, here's a breakdown of the same overhead of the Stamp and Falcon running on the same model at XNet. As shown, the overhead for nonlinear layers is significantly reduced, although there is indeed an additional overhead on the LTH side. In conclusion, STAMP shows that even tiny secure hardware with very limited performance can be leveraged to significantly speed up distributed privacy-preserving machine learning protocols, if the protocol can be carefully designed for lightweight trusted hardware. Thank you for your attention, and I look forward to your questions.